Okay, so yeah, thank you very much, everyone, for your answers there. We're going to start off this morning. Our first speaker is Pierre Kwan. Pierre is a senior water treatment technologist and has been with HDR's Seattle office for the past 20 years. He has designed water treatment systems throughout the world, ranging as small as 10 gallons per minute groundwater systems for a remote Alaskan village, accessible only by seaplanes, up to 200 MGD direct reuse plants in the Middle East. He is a registered professional engineer in multiple places, including Washington and Oregon. He obtained his Bachelor's of Science in Civil Engineering from Ohio State University and his Master's of Science in Civil Engineering from the University of Washington. So Pierre, I think you should be able to share your screen and present your presentation.
Yes, Jolene, can you see my screen? Can everyone see my screen?
Yes.
Okay, great.
Okay.
We'll get started.
Okay, thank you, Pierre.
Okay, thank you, everyone. Oh boy. Do you see the full screen, Jolene, or do you see like how I present it like on PowerPoint?
It's showing your speaker view.
Okay. Let me try something else. Hold on just a moment.
Maybe in display settings.
Okay, does that work?
Yep.
Perfect. Thank you, everyone. It's a brand new world here. We're trying to accommodate the challenges everyone's facing right now. So once again, thank you for joining in today's water treatment presentation. The title of my presentation is Advances in PFAS Treatment, Bench, Pilot, and Full-Scale Results. I'm going to do 3 case studies here of projects we've been working on, specifically dealing with PFAS. Quick agenda. Since I'm first, I thought I'd just give a 1 or 2 slide description of what are per or polyfluoroalkyl substances. Those are the PFAS compounds. Initial overview of what a lot of utilities around the country, even around the world, are doing for PFAS treatment. And then I'll dive into 3 case studies to show actual full-scale performances, or pilot testing, bench scale testing, full-scale performances, and some wrap up with some summary and conclusions for this morning. PFAS. What is it? Why is it such a concern? Broad overview, PFAS is a compound that is a man-made compound, and there are multiple routes of it getting into the environment. It could be the use of aqueous film-forming foam. Try to say that 3 times fast. AFF is a common firefighting foam used extensively to putting out fuel fires like jet fuel, diesel, gasoline. PFAS is used in a lot of our modern environment, and it shows up in a lot of industrial discharges. We are finding it in man-made materials, and as we throw it into the trash, we find it's showing up in landfills and then getting into leachate, and then it also shows up, it goes into our sewers, sanitary sewers, then into wastewater plants, and the solids coming out of wastewater treatment plants, when land applied, are now putting that PFAS into croplands, and it's showing up in some of our foods. So you can see it readily enters surface waters, groundwaters, and as a result, it's showing up in many of the drinking water supplies throughout the US and the world. There's a huge family of compounds related to PFAS. It's over 1,000 different compounds have been identified. The most common of which are 2 specific ones: PFOS, PFOS, and PFOA, PFOA. And there's the schematic design or chart showing these molecules. They do have health impacts. the EPA has established a HAL, health advisory level of 70 nanograms per liter, of which if you're above that, the EPA recommends, but it's not an MCL or a secondary MCL, but they highly recommend treatment. Now, many states have gone above and beyond that, especially, and I'll point to it later, Washington have proposed lower levels, acceptable levels of these compounds in drinking water. These compounds exhibit hydrophobic and hydrophilic properties, so that means they're, in essence, they're difficult to remove in many cases. Conventional treatment using coagulants or disinfection are not very amenable to removing these compounds. And the worst is they're highly soluble and stable in water. Once it gets into the aquifers, once it gets into the rivers, it moves quickly and it does not degrade with natural bacteria. And so they exist for quite a long time. And as a result, they're not easily removed from water. They persist. And that's why a lot of drinking water utilities around the world are so concerned about this. This is a brief overview. There's, you can look at past Northwest AWWA presentations. You can look at national AWWA and even EPA presentations for what these compounds are and what they mean. But I'm going to really focus on treatment today, this morning. There are the 4 major categories of common PFAS removal technologies currently in use, starting with activated carbon that can be found in both the granular form or powdered form. And that does a good job of both removing both PFOA and PFOS to greater 90% removal. Anion exchange, that's a type of ion exchange resin. These are special plastic beads, plastic resins that are specifically manufactured for removals of these compounds. PFOA, 10 to 90% on the formulation. PFOS is rarely removed to greater than 9%. Membrane filtration, and here I'm talking about high pressure membranes, reverse osmosis or nanofiltration to remove these compounds. They low pressure membranes, the ones like microfiltration, ultrafiltration, have zero removal for these compounds. We're very specifically talking about high pressure membranes to remove these, and they do they remove these compounds very effectively. And then advanced oxidation, this is a combination of high energy UV and the addition of a compound catalyst such as hydrogen peroxide to produce very energetic molecules that actually attack and degrade the molecules, breaking them down. Literature shows that PFOA has less than 10% degradation, PFOS 10 to 50%. It's all depending on the energy, the amount of UV energy used, the amount of hydrogen peroxide injected in the water, as well as other constituents in the water. These are the 4 most commonly discussed, but especially here in the Northwest, I'm going to focus on the top 2, activate carbon and anion exchange for the rest of this presentation. So the first case study is going to be discuss East Coast utility. Because a lot of the sensitivity related to PFAS and its occurrence, and especially in drinking water, this utility has offered to share the data. They just didn't want to be named in the presentation because of the issues they're dealing with. For this one, this utility is a comprehensive surface water study. They're finding it actually in the rivers and in the reservoirs that they draw from for their treatment plants. And they really want to investigate the occurrence of PFAS using powder activated carbon, PAC. That's a system they already had. And what does it mean? And then advancing towards the fate and transport of these compounds in the environment. So it's studied with a watershed investigation, UCMR3 That was an EPA study, initially determined PFAS in their watersheds in over 20 locations within the watersheds. It was a 2-year investigation. They found 11 different PFAS compounds in the water. So then it was adding a PAC system, or expanding a PAC system. They had one, it was to expand it. It was easy to implement. Like a previous slide shows, initial literature showed that it was effective for PFAS removal, but they were wanting us to help identify what the residual handling challenges, and it is expensive to operate. Powder activated carbon isn't cheap. You're using it, use it only once, and it goes into your residuals that then has to be managed. And from there, looking at fate and transport model. Exactly when do these detections in the watersheds move, and how quickly do they move to the surface water plant's intakes? And then from there, identifying what additional treatment, if needed, to come to a permanent low-cost solution. So let me show some of the results. And first off is powder activated carbon jar testing. We tested 2 different powder activated carbons in different doses. The source for this jar testing was the RWPS, the raw water pump station, and 2 carbons, water carb 800, water carb 1000. These are 2 carbons that were vendor claims said they're very effective for PFAS removal. And you see that by the time we get into the plant, there's a little bit of dilution, and we show that even without any powder activated carbon, we saw a little bit of reduction, and that's solely through dilution with other waters coming into the plant. And then we tested 10, 20, and 30 milligram per liter of carbon, and you can see it was a linear decrease in PFAS plus PFOA concentrations as we added additional powder activated carbon. The other thing we had tested was in jars using a dose of just 20 milligram per liter powder activated carbon. We saw effectively no change in removal based on contact time. We see that in this chart, we get about 50% or slightly greater than 50% removal for both carbons with only 1 minute of mixing time, contact time. So we just add it into the rapid mix, goes through the flocculators, and out it goes. And we see half removal. Then extending that to 60 minutes, and that's all the way at the end of the sedimentation basins. We saw no real or minor additional removal with the water carb 800 carbon. And we see better removal with water carb 1000, but still the vast majority of the removal occurred in that first minute. The additional 59 minutes provided some, but not substantially greater removals. So and then taking these results, going into the full scale system, we decided on the 20 milligram per liter dose with the water carb 800, and we see total PFAS. This is the summation of all 11 PFAS compounds found in the full scale plant. We saw a 42% reduction between the raw water and the filtered water. And when it comes to specifically to PFAS and PFOA, we saw a 38% reduction. Now, the difference here between the 2 charts, the one on the left and one on the right, is total PFAS is, again, all 11 compounds that were detected. Whereas PFAS plus PFOA in this particular state is the values that the state regulators were requesting the utility to report for compliance. So this points to one of the things with PFAS regulations is PFAS plus PFOA and a couple others in the Northwest are the ones that are regulated, but there are many more types of compounds that aren't currently regulated or being proposed to be regulated. So when testing for these, do consider looking at the whole suite of PFAS compounds that you find. A second case study, different state, similar situations. They wish to share the data, but didn't want to remain anonymous for now. They looked at activated carbon, granular activated carbon, side by side with ion exchange. You can see by the photo here, these were systems procured through Calgon Carbon, and we packed them into large vertical pressure vessels and monitored the performance. In the photo in the center bottom right, we had different sampling ports to track breakthroughs 25% through the bed at the halfway point, 75%, and we also tested on the vessel outlets for both these carbons. In this particular test, we see the influent, and it's very, very high doses. So this is showing total PFAS of in the upwards of the 3,000 nanograms per liter. Again, bear in mind, the EPA health advisory level is 70. And so the raw water was over three orders of magnitude higher than that advisory level. We see in this test that the blue line in the middle, that is the outlet from the ion exchange. The red line at the bottoms, that's the outlet for activated carbon. We show ion exchange immediately breaking through and increasing, as opposed to the granular activated carbon, which had to complete removal, so therefore non-detect at the outlet for the first month of testing. And then once it did break through, its release, its outlet concentration, which was much at a higher rate than ion exchange. So by the end of the 4th month of testing, you can see that both medias were still removing the PFAS compounds, total PFAS compounds, but activated carbon was breaking through quicker. And so at the end of the 4 months, the removal was exactly the same. Though ion exchange broke through quicker, its rate of breakthrough was slower. One big point to note in this is one of the benefits for ion exchange versus activated carbon is empty bed contact time. You could see at the top above the chart, in this test, the granular activated carbon was being loaded up 4 times or 5 times slower than ion exchange. This means that if all things being equal, that the activated carbon media we need for the same empty bed performance would need 5 times the amount of carbon versus ion exchange for treatment. Now, focusing on long chain versus short chain PFAS. Again, I told you there's a universe of different PFAS compounds out there, and what this chart is showing is the different types of PFAS that were determined, and it was really clear for this test that we're seeing very specific compound removal. The orange line at the very top that goes at the 100% and moving across the top, that is both PFAS and PFOA. So across the entire duration of testing, we're seeing 100% removal of both PFAS and PFOA. And in the table, you see the different PFAS compounds, and the number after each compound is the number of carbon carbon atoms in each molecule. So it's an indicator of how long the molecule is. And what this chart is showing is that we're getting extremely good removal for the longest chain compounds, PFOS, PFOS, and PFOA. But as the molecular chains got shorter and shorter, we saw worse and worse removal. So in this case, the granular activated carbon system was very preferentially removing long chain molecules and doing actually a not so great job at removing the short chain molecules. And in this particular state, which is the utilities in, the regulators wanted to see removal across all the different molecules. They're currently regulating to PFOS, PFOS, and PFOA, PFOA, but they wanted to see all the results. And then one common use of activated carbon is for TOC removal. That is the blue line at the bottom. And this is an indicator that using total organic carbon, which is a compound we commonly measure for treatment for different purposes, it's not a good indicator for PFAS removal at all. You can see that its removal started off only at 80% right off the bat and decreased to 40%, and it didn't correlate to any of the PFAS compounds that were done in this test. Finally, let's go to third case, which is over in Issaquah, Seattle suburb, the Gilman wells. In 2013, 2014, they detected very high concentrations of PFAS, specifically PFOS. And unlike the prior charts, which were nanograms per liter, this is table is in microgram per liter, which so you to make the prior data match with this one, just move the decimal point 3 times over. So this they detected PFOS at 0.6 and 0.5 microgram per liter, or 600 and 514 nanograms per liter. At this time, the EPA provisional health advisory was 0.2 or 200 nanograms per liter. Now that's, again, the prior slide set is now down to 70, and I'll show that the state of Washington has proposed lower numbers. So in any case, the PFOS compounds were much higher than all the limits, and we do see a smattering of other PFAS compounds in this water. So this is a system that went into full-scale design and installation immediately. 2 vessels, lead lag configuration. We started off with by having the vessels, 1 vessel filled with bituminous coal and 1 with coconut shell carbon, in order to test full-scale testing immediately of which carbon acts better for removal. 20,000 pounds of carbon in each, and system is currently designed for and operating at 250 GPM, expandable to 1400 GPM if contamination was found in other wells at this location. So right now at 250 GPM, empty bed contact time of 21 minutes. And this system is installed in 2016, and since then, let's start with the table at the bottom. We saw a difference between coconut carbon and bituminous carbon. The coconut carbon was only in use for 11 months before we started seeing breakthroughs or concerns with its performance. It processed 102 million gallons before needing a change out, and that equated to 19,000 bed volumes before change out. Now compare that to the bituminous coal. It was installed 36 months and counting. In conversations with the city, they'll expect to start changing out that media sometime this winter. So we can easily add another 6 months to that. So as of last month, they processed over 340 million gallons with this carbon, and so it's over 63,000 bed volumes. So when it's all said and done, we could easily estimate 4 times the performance of bituminous coal in this full-scale test versus coconut carbon. Now because of that issue, both vessels are filled with bituminous coal. This is a chart showing PFAS concentrations, showing that we saw very high concentrations prior to the start of the system. The wells weren't in use. PFAS concentrations, you can see it was up to 0.6 microgram per liter or 600 nanograms per liter with the treatment system on in June of 2016, and now the well's constantly pumping. You see the first trend is with continuous pumping and these compounds not being the sources of these compounds no longer entering the aquifer, the raw water concentrations are going down. Basically, this is a pump and treat system. We're pulling the contaminants. The city of Issaquah is pulling the contaminants out of the aquifer, removing those PFAS compounds, turning them into drinking water. See the dash line for media change out. And this chart is shown specifically for the coal, bituminous coal. Here we see now lead vessel port 2, that is the halfway mark for the filters. So we're seeing after years of use, and we're seeing now in just the last 2 months detection of PFAS at the halfway point of the lead vessel. And you can see here we're still below the 70 microgram per liter. Or I'm sorry, the 70. I'm sorry, I screwed up the units. 70 nanogram EPA action level, but we've at the halfway point have gone over the 15 nanogram proposed Washington DOH state action level. While that full-scale carbon testing was occurring, we also tested ion exchange at the using the same wells. This was a resin called PSR2. It's a specific resin found to be very effective for ion exchange removal with PFAS. And we see here is a little pilot unit. And I want to note the tall cylinder on the right, the beige cylinder on the right, that is the ion exchange resin. It came in slightly beige, somewhat translucent plastic beads. I want to point to that color later on, but you can see right now at the start of testing, it is pristine beige looking color. Pilot testing conditions, we loaded up the resins, really focus on the bottom line, which is empty bait contact time of only a minute to really run the water through, versus the full-scale system, again, at 21 minutes. Again, another benefit of ion exchange that's claimed is that you can load it much faster reactions than therefore smaller vessels. But in Issaquah, what we found is differential pressure. We saw that pressure really increase over time and reaching over, starting clean filter differential pressure at 4 psi, increasing to 12. And this is actually over the course of just a month. And the reason for that is we're finding that there's iron bacteria in the well. It's naturally occurring. It's always been there. We did sent the bacteria off to labs. We found it's non-pathogenic. It's not a health threat, but it was specifically clogging the ion exchange resin. And what you see up on the upper right is a picture of the virgin resins versus the bacteria that have been scraped off of them. And that's that brown, looks like yarn That's the bacteria. And then what you see at the bottom right-hand corner is a photo of the column zoomed in. The beige-looking material at the top, that's actually the water that's been stirred up. The brown stuff at the bottom is the resin coated with this bacteria, and it was just plugging everything. This resin, this issue wasn't expected, so we didn't have an ability to backwash the pilots, and so the alternatives came up was pre-chlorination and dechlorination for the resin, or high energy UV to kill the bacteria. But given these issues, and this was the purpose of this testing was to move forward with full-scale design of their centralized treatment plant, the city decided to not pursue this and continue with activated carbon. Here's some of the results. Again, really good removal. And here's the summary. We started testing in March of last year. We ended it in May because of the differential pressure. We sent the water samples to the lab to continue testing, and based off the lab, if we could kill the bacteria, they can claim that we can reach 600,000 bed volumes versus before PFAS breakthrough. Again, compared out to 36,000 bed volumes in the testing that was done with bacteria. And again, the photo here is showing the column. You can see down the bottom is the initial beige color, and the top part of that column is all red, brownish red. That is all the iron bacteria. So in summary, PFAS, we find it everywhere, a lot of industrial and commercial applications. It's now entering the water supplies. It has unique chemical and physical properties that makes it persistent in the environment and difficult to remove. We talked about activated carbon and ion exchange today as removing PFAS. High pressure membranes also work. I just don't have time to talk about that. And specifically, iron bacteria is more detrimental for ion exchange than activated carbon in this testing. The final takeaway points, all waters are unique and should be tested. There are a lot of different compounds you should look at, but besides just PFAS, to identify fouling. If possible, you want to test different resins, ion exchange resin and activated carbon to look for performance. You want to run it until you see breakthrough, and look at multiple ports in columns in order to understand breakthrough patterns. And I didn't discuss nanofiltration RO in this slide, but if you do test it, one very serious consideration to look at is how do you manage that concentrate, because that residual brine is now very high concentrations of PFAS. So with that, I'm wrapping it up. My contact information, and I'll turn it back over to Jolene.
Yeah, thank you, Pierre. So we did have one question come into the chat box here, and I think we do have some time, a couple minutes here to answer. So Pierre, the first question is, if you pre-chlorinate, do you need, if pre-chlorination, do you need to pre-filter?
For groundwater, no. You don't need to pre-filter if you pre-chlorinate. What you actually do need to do and consider, though, is if you use activated carbon is sensitive to chlorine, because the chlorine will, high concentrations of chlorine will actually attack the carbon, change it from granular activated carbon to powder activated carbon, and bleed through or pack the bed full of fines and cause head loss. So there is a limit of how much chlorine can be applied onto GAC, and the number varies between types of carbon and manufacturer and warranty conditions, but a good rule of thumb is about 1 milligram per liter going onto the carbon. Now, if you use ion exchange is very sensitive, even more sensitive to chlorine than carbon. You need to fully dechlorinate the water before you apply chlorinated water must be fully dechlorinated before it can go on to ion exchange. Otherwise, the plastic of that resin will fracture and you'll turn the individual resin beads into a giant bed of goo.
Okay, that sounds like something you don't want to do.
Yes.
So Pierre, thank you very much. We do have a couple other questions that came in. I'm hoping that we can answer those kind of offline on the side, but I do think we need to move on to our next set of speakers. But thank you very much, Pierre. That was a great presentation.
Okay, thank you.
So next up, we have Mike Tollering and Kathy Swanson. Mike is a water treatment specialist focusing on filtration systems for the treatment of organics and inorganics. He has over 20 years in the water treatment field, working with both municipal drinking water as well as industrial clients, including semiconductor, petroleum and chemical refining, power, construction dewatering, and remediation. Mike has extensive experience in the design, operation, and service of GAC and IX filter systems. He received a BA from the University of Pennsylvania, go Quakers. After playing college ice hockey, Mike began his career working in marketing for the NHL's Hartford Whalers and New Jersey Devils before beginning in the water treatment industry with Amoco Oil. Mike lives in beautiful Anacortes, Washington, after 15 years in Portland, with his wife, 2 children, and golden retriever pup.
Darn.
Kathy Swanson is a groundwater remediation specialist and the West Sales Manager for Purolite Corporation. She has worked in the water treatment world of perchlorate, nitrate, uranium, TOC, VOC, and now PFAS removal for the last dozen years at Purolite and previously at another company. She has worked on treatment technologies ranging from GAC to biological to reverse osmosis, but her true focus has been ion exchange resins. Her project portfolio includes both remediation and drinking water sites. She received her BS in chemical engineering at Northwestern University in the Chicago area and is just finishing up her MBA from UNC Chapel Hill. She is a frequent speaker at PFAS educational events, including the American Groundwater Trust, American Waterworks Associations, and others. So thank you, Mike and Kathy, for being here and presenting for us, and go ahead and take it away.
Thanks, Jolynn. I think we're out of time now after the bios. I guess we could have cut those shorter, but yeah, I've been in the industry 20 years. Appreciate the opportunity to present for everyone. Thank you for being on the webinar. I've worked for some of the larger water treatment filtration companies in the industry, and about 4 years ago opened up my own company called Environmental Site Solutions. We provide filter system design and systems, including activated carbon and ion exchange systems, and we provide turnkey change-out services for that around the Northwest and in Hawaii quite extensively. Kathy?
Hey, thanks, Mike. A little bit about Purolite. We're one of the only companies that focuses 100% of our attention on resin technology. We've got 1,100 employees, over 2,000 products, but most importantly, over 20,000 customers like you guys. So we have ion exchange for all kinds of applications, but today we're going to talk about potable water and groundwater with PFAS.
So here's our quick agenda. Some of it, Pierre did a wonderful job speaking about PFAS overview. So we'll touch on the slides. We are going to breeze through rather quickly so we have a little time for questions, but the agenda is listed here, and we're going to go more maybe into the design, system design, and economic evaluation as well.
So for those of you that aren't as familiar with PFAS, it's called the forever chemical because, as Pierre mentioned, it's bioaccumulative, it's resistant, it's environmentally resistant. If you want some more background, I do recommend the movie Dark Waters or the book Exposure. Both of them feature Rob Balot. He is the lawyer that basically brought a case against DuPont for contaminating the groundwater in a town in West Virginia. That chemical was PFAS, and that has led to a lot of the regulations that we have today. So why do we care about PFAS? Really, it's because part per trillion in the water is part per billion in the blood. And I can confidently say that probably everybody on this call has some PFAS in their blood. It's been found basically 100% of people in LA area where I live. And then in remote corners of the globe, everything from polar bears to whale livers. So it's pretty pervasive. Very quickly, I know we've touched on this, PFAS can be any one of almost 5,000 chemicals under the category of per and polyfluoroalkyl substances. We focus from a regulatory standpoint on PFOA and PFOS. EPA test method 537.1 looks at 18 different PFAS chemicals. Again, the PFOA and the PFOS are the ones that have gotten the most attention, but some of the other PFAS are getting regulated by the states a little bit more tightly.
So,
Mike, you want to talk about this?
yeah, sure, Kathy. So here are the most common technologies for treating PFAS in drinking water. I'll start at the bottom with RO membrane. Although there are some systems out there, there are some significant downsides too. The cost is quite prohibitive. In addition, you have to treat a reject stream of about 25% of the water that's heavily concentrated. So that usually is very difficult, and they're very energy intensive. So we haven't seen too many RO systems for drinking water applications. The most common are activated carbon. We're going to be speaking more about granular activated carbon systems. Pierre mentioned powdered activated carbon as well, and then the single-use ion exchange resin. Both activated carbon and resin are common. Great slide. You can see here currently about 51% or 50% of the treatment systems are carbon, about a third ion exchange, and then much lower would be RO or oxidation. I think it's important to say that as ion exchange is getting more attention here, we're seeing the numbers growing for ion exchange because it does have some significant benefits over activated carbon that we'll talk about a little bit later. Go ahead, Kath.
The regulatory trend here is really to see almost non-detect. You know, even though the federal level has dropped from the 400, 200 for PFOA, PFOS to combined 70 part per trillion for combined PFOA, PFOS, a lot of states have lower regulatory levels. I don't know, it seems to advance on its own. I apologize. For example, Washington. I thought I got rid of that. I need some PowerPoint lessons. But obviously, the Washington has a DOH level of the 15 nanograms or part per trillion. Like I mentioned, I live in California. Even though we have a notification level and a reporting limit, as you can see on the chart, we're still being asked to have non-detect, basically on the lag bed. So there's two different removal mechanisms that we see with these two different medias. The first is absorption, and then with ion exchange, you have both absorption and ion exchange. And we're going to get into those a little bit. Take it away, Mike.
Yeah, so with granular activated carbon, and this is kind of the industry slide, but it shows here a good representation of pore structure within within activated carbon. Activated carbon is an amazing material, has a incredibly large amount of surface area. So Kathy mentioned absorption. Activated carbon works via absorption, and because of the enormous surface area, it has enormous capacity to absorb or dissolved organics. We'll talk a little bit more about design and empty bed contact time and mass transfer zone and how activated carbon works. But here we go. What industry-wide we're looking at is about 10 plus minutes of empty bed contact time for treating PFAS. Other organics, you can run carbon at a shorter contact time, but we've seen 10 to 15 minutes is pretty normal for empty bed contact time design for PFAS systems. Carbon has the other advantage of if you have to take out other organics, whether it be chlorinated solvents or VOCs, carbon will take out those organics as well as the PFAS. The challenge with carbon is it will also remove other organics, or TOC. TOC is kind of a generic term for organics in water, dissolved organics, which comprises hundreds of different organics. So that will compete to take up space in the carbon. Also with activated carbon, it does an amazing job on long chain PFAS, not as well on the short chain, as we'll show in the upcoming slides. And another nice thing about carbon, as we mentioned, is it's been used for years and has hundreds and hundreds of sites, and is very common for PFAS treatment.
So how ion exchange works. This is kind of a peek into my brain. I know that's scary, Mike, don't say anything. So you have a resin bead and it's got sort of little hands or magnets on it. And those magnets are holding a mobile anion. And in this case, it's chloride. So the ion exchange, it basically kicks off the chloride and the anion from the PFAS joins to the resin bead. So that's the first mechanism that's very fast, which gives us the fast kinetics, and it's very strong. So it's a very tight connection. The second thing that happens is that there's this long carbon tail, and then the resin bead is also made up of polymers and plastics. And so there's an entanglement between that long carbon tail and the resin bead. So it's an extremely tight bond and very high selectivity. So how does it know to kick off the chloride? Basically, it's a function of the selectivity. So, whoops, there we go. So as you can see, you have your normal TDS in the water, nitrate, sulfate, chloride, and those are in the water like 1,000,000 times more than any of the PFAS, generally speaking, for a drinking water application. So as you go up this arrow, the resin becomes more and more selective. As you can see, anything with a sulfonate it's more selective for than the carboxylic acids, and the longer chains are selected better than the shorter chains. And how do we know that? Well, here's some data that shows that. So this is a 6-chain, 7-chain, 8-chain, 9-chain carboxylic acids, and as they get longer, it gets absorbed better. And then we kind of see the same trend with the sulfonates. So 4-chain, 6-chain, 8-chain, where they're basically at non-detect out to 300,000 bed volumes. So with resin, you want to make sure that we're looking at a PFAS selective single-use ion exchange resin, because other anionic resins can pick up PFAS, but they won't do it to the extent that a PFAS selective resin will. Purelites is called PFA 694E, so if you see that in this presentation, it's pretty much synonymous. It can treat to 99.99% removal. The capacity is really determined by those other competitive anions in the water, so nitrate, sulfate, chloride, etc. And as Mike mentioned, it's pretty effective on both long and short chain, and of course it's NSF approved. I put this in here just to show you. So it's really those other anions that are really determining the throughput of the resin bead, because the PFAS, it's extremely selective for PFAS, but it's in the water at a very small amount. It really only takes up about 1% capacity of the bead, where all those other anions are really determining the full capacity of that resin bead.
Great. So now we're going to discuss a bit about design of a system. I can't stress enough the importance of water quality testing and analysis prior to the design. So we'll talk a little bit about water chemistry as well as modeling and piloting for system design.
So with the water chemistry that Mike alluded to here, if we have a very good water chemistry, we can accurately model ion exchange resin. So I'm going to give you a couple examples here. The dashed lines is our modeling. The solid lines is our actual. This is a system on the East Coast, and the East Coast has embraced PFAS treatment a little bit earlier than we have out west. But as you can see, the correlation is fabulous between the model and the actual. This is another site. This is our Warminster site in Pennsylvania. What's interesting about this site is that the inlet has plus or minus 25% variation in the PFOA. The dashed line, whoops. The dashed line again is the model, and the solid line is the actual. Extremely good correlation. And this is another system in Pennsylvania where the influent had even greater variability. And then the effluent, you see a little bit of noise, but here is our model, which is both conservative and accurate. So this would be for ion exchange, a typical throughput model. This would be a Southern California site. Generally speaking, you know, even though we have many PFAS in the water, generally PFOA is going to be our driver for changeout because it breaks through before the PFOS. A couple things to notice here, you know, it's a lot of times we get the water chemistry from you, but then we're not sure what the endpoint is. And, you know, if people are shooting for non-detect, that's a different point than if they're shooting for, you know, a 15 total PFAS or so on and so forth. So that's an important thing. So here, what we looked at is, and I want you to remember this number for later. So at 10 part per trillion, we still have non-detect on the lag, and we'll get about 280,000 bed volumes in this example. So we're going to go through an example in a little while, and I just want you to remember that number. And like Pierre said, there's a difference between the water in Southern California, the East Coast, and the beautiful Pacific Northwest. Up there, you guys have very pristine water. You have very low TDS, low chlorides, low sulfate, and your throughput volumes are much, much higher. So you can get, like they predicted, it was a different company from that pilot, but you can get extremely long throughput with waters like you guys have.
So Kathy mentioned modeling. Modeling can be done really effectively for ion exchange resin, not so effectively for activated carbon because there's so much in the organics or the TOC. There's so much different type of organics. It's tough to model the PFAS. So really, although we do need water chemistry for carbon, really we'd be looking at either bottle point isotherm test in the lab or running a rapid small scale column test, or RSSCT, which is a very common test for activated carbon. That will help us show throughput and model how long carbon will last. So that's really the first step, and then after that we look at pilot systems, which we'll talk about briefly. So here's a pretty common setup, and I've seen lots of different designs, but this is a common setup for piloting. Those columns you can put either activated carbon or resin or both in, and then scale the system to the similar scale of a full-scale system. As you can see, something to note, this takes time to see breakthrough, could take weeks, months. So what is done typically is there's sample ports put in at 25%, 50%, 75% of the bed to cut that breakthrough time. So if we're looking at results after 25% of the bed, it's going to cut that time much shorter. There is a cost and a time that it takes to do a pilot, but we always highly recommend doing pilot systems. This gets into a bit of the design considerations, as was mentioned with Pierre and in our presentation earlier. The difference is quite significant in empty bed contact time. Resin is roughly 2-minute empty bed contact time recommended. Carbon, roughly 10 minutes. So as you can see, for the same flow rate, you would need a system of carbon that can handle 5 times the empty bed contact time, or five times more media in the bed. Kathy? So here you can see a good comparison on a 350 GPM system. For ion exchange, although we had 4 vessels, they were 4-foot diameter and 8 foot tall. For the carbon system, you did a much, much larger system. This was I believe, a 10-foot diameter by roughly 20 feet tall. So significant, about 5 times more media so this is a resin system with smaller vessels. I think we had about total of 240 cubic feet of media, Purolite resin in these. And for the carbon system, we had probably plus or minus 5 times as much activated carbon per cubic footage. So you can see the difference in footprint and the same size or the same flow rate type system. One other thing with carbon, and Pierre mentioned this with resin, so this is an interesting, typically when we do a carbon system, we recommend backwashing the system at least before startup and potentially during operation to reduce pressure drop. So sometimes, a backwash tank, or there is some capital equipment needed to plan for backwashing. Yeah, go ahead.
So the difference becomes even more dramatic as you go into higher flows. For an ion exchange 2000 GPM system, you can get away with one high flow 12-foot system with 840 cubic feet of resin on site. For GAC, if you're using 20,000 pound vessels, you would need 8 vessels and somewhere between 5,000 and 6,000 pounds of GAC. So like Mike mentioned, you're using 4 to 6 times more media with GAC than ion exchange.
So this shows just the runtime, and also regarding sustainability, there's a lot of talk that activated carbon can be reactivated and reused, which is tremendous. It's an amazing property of carbon. So it is quite sustainable. However, it needs to be changed out a lot more often than a single-use resin. So although you have the ability to reactivate, there's a lot of energy in sending it to the kiln and reactivating and returning it. So they're both medias are sustainable in their own way. Resin because it's changed out so infrequently, and carbon because it can be reactivated. This is just mentioning for an ion exchange system, if you want to run it seasonally, it's not a problem. It can be run mothballed and then put back online just with a quick flush. With activated carbon, it does have potential to grow bacteria. So we do recommend, if you're going to take carbon offline for a period, then we would recommend doing some sort of sanitization or a caustic wash in order to kill bacteria before putting it back online.
One of the things that we have seen with GAC is that because it's not selective for PFAS, it can slough or dump shorter chain PFAS. And you can see in this example, essentially this is PFBA, which is the shortest of the carboxylic acids, the 4-carbon carboxylic acid. So it comes in, and as the other PFAS are loading, the effluent concentration is almost double the influent concentration. So the influent's probably around 200, 250. It's coming off at 400 part per trillion. And that is not just seen with PFBA, but it's literally seen with every single one of these PFAS shorter chains until you get to your trigger change out for PFOA. So that's something to just keep in mind as you're looking at different technologies and as you're looking at what states are looking at for regulations. For example, for PFBS, that's part of the EPA's 4-point action plan. Number 4 is evaluating Gen X and PFBS. And as you can see, the PFAS selective ion exchange resin lasts extremely long time compared to any kind of GAC. I know we're showing the coconut here. We did try the coal. I think it came out maybe, a couple hundred bed volumes later. So this is a huge differentiator on the sulfonic acids, especially between GAC and resin.
So Kathy, we need to breeze through this quickly, so I'll let you run through it, but we only have a couple more minutes to go.
Okay, we're gonna fly through this, guy. So I wanted to drag you through an example so you can see what we're looking at between different designs. So if we were looking at a 2000 GPM system, a couple things I want to point out here. Like I pointed out before, you have 4 times the amount of equipment, and this is only a 9-minute empty bed contact time, but it's still within the range of acceptable for GAC. Now, in terms of throughput, this is actually a real system. They were using ion exchange. They were getting 35,000 bed volumes. We estimated 280,000 for ion exchange. Looking at those numbers, you know, you have half the footprint, but you're also consuming 8 times more media. Now, if I change to 40,000 pound vessels instead of 20,000 pounds vessels, as a lot of people have, now it's only half the footprint. The vessels are a lot taller, but I want to point out that you're still consuming, even with bigger vessels, you're still consuming the same amount of media. That still means 8 slurry trucks as opposed to 1 every time you do a change out. Go ahead, Mike.
Oh, and here this just shows a O&M comparison of ion exchange versus GAC. So because of the usage of more carbon, you can see the costs, and if you look at the operating costs, dollars per 1,000 gallons, you see resin slightly lower at 13 cents per 1,000 gallons, carbon a little bit higher at about 18 cents. So that's operating costs. Capital costs, because of the additional size and equipment needed, carbon is usually more expensive. We figure that ion exchange system is somewhat, or maybe a half to 2/3 the cost of a carbon system for capital costs, because of using you know, just 1/4 the size. Yeah. So that's an example of the size. Just to go through carbon and ion exchange, this will be a refresher, but ion exchange, smaller footprint because of the faster empty bed contact time, longer throughput from 3 to 20 times, you know, depending on the data from different sites. Ion exchange resin has a better uptake of short chain PFAS, typically slightly lower capital cost, can be modeled using water quality analysis. The challenge with ion exchange is if there are a lot of other anions in the water, they will compete. So that's a summary of ion exchange. For carbon, removes other organics. If you need to target other organics, that's a good thing. If it has high TOC in the water, however, that's a problem because it will reduce capacity for PFAS. Carbon is less susceptible for suspended solids because it has a lower pressure drop. So the issue with that is a little bit different, and it won't filter out as much particulate. As we mentioned, you really need to run a pilot in our RSSCT because we can't model carbon as effectively as resin, and it can slough off the shorter chain PFAS. It is also a very well accepted and efficient technology.
Whoops, there we go. There's our last slide, Mike.
Yeah, so that's it. We can take questions if there are any. I think there was one.
There's a couple questions, and I want to leave you with a couple things. Water chemistry, I think Mike said it, and we can't say it enough. Water chemistry is huge. So obviously, Pierre presented a case study in the first segment that showed ion exchange didn't have quite the same throughput as carbon. It would be interesting to look at the background water chemistry, and that could be one of the reasons why. There's a question here from Mr. Townsend saying that the previous presentation said that ion exchange grows bacteria. I don't think the presentation said that ion exchange grows bacteria. There are actually billions and billions of gallons a day of water, potable water, being treated by ion exchange in that particular pilot, they had iron and they were getting some iron-eating bacteria. In my experience, and I've been doing this for a long time, generally speaking, that is coming from the well. And, you know, this is very similar to in California, we do a lot of perchlorate treatment. It's very similar to that, where we have resin that's sitting in the field for a long time, and resin is a very good filter. So if you start getting bacteria in your well, you are going to get it into your resin. So that would be something that needs to be cleaned up. And at the same time, you are looking at 10 times more throughput between the GAC and the ion exchange in that particular example. So it might not be that big of a deal to put in some preventative measures and really reap the benefits of ion exchange long throughput. So pressure losses, what kind of pressure losses would be expected for drinking design example for the PFA 694E? It is slightly higher than carbon. If you look only at a resin bed, it's about 1 PSI pressure drop. Yeah, 1 PSI per linear foot. So somewhere in the 5 PSI, and then you have to add the equipment. Carbon's a little bit less than that. It's all in the economic evaluation though. And I've done this example before where I took into an account, I took into account pressure drop versus longer throughput, and the longer throughput really trumped the increased pressure drop.
And
I
would, sorry to interrupt, I would also
Yep.
say that pre-treatment is key. So regarding pressure drop, we're talking about clean media or fresh media. So really, and especially with surface water, pre-treatment to get out any TSS is very crucial to reduce or keep the pressure drop as low as possible and reduce energy costs.
Yeah.
Last question, won't TOC affect ion exchange and carbon to the same extent, Kathy?
Yeah, I would say that TOC does affect both GAC and ion exchange, but ion exchange is affected a little bit less than GAC. If you look at a site like the one down in Florida, GAC, you know, they had somewhere between 8 and 12 ppm of TOC. GAC was, I mean, basically maybe like 4,000 bed volumes. It broke through extremely quickly. Whereas ion exchange, where it should be getting 200,000 bed volumes, if they were to take the TOC out first, it's only getting about 60,000 bed volumes. So yes, it affects it, probably, you know, quite severely, but it's not to the exact same extent for both. And I, again, would recommend pre-treatment for either.
So I think we're out of time. Both Kathy and I work closely. They're a very valued vendor for us. Both of us are happy to take questions offline. I think we're out of time, but our contact information is there. And if you want to contact either or both of us, we're more than happy to work with you. We're actually nice people. You probably can't tell that, but we are. So thank you for letting us present. Appreciate it.
Yeah, thank you, Mike and Kathy. Yes, we are out of time for this first session here. So we will take a quick, how about, let's say a 5-minute break. And then we will, looks like I still need to get our next speaker lined up to go when we start back again. So just a reminder to folks that may have joined late, if you are needing CEUs, be sure that you put in the chat box your name, the state that you're from, and your either your operator certification or license number. So if you could do that, and then we will start back up here in probably about 5 minutes or so. And yeah, thank you.
Hello? Could I, okay, hang on a second here.
Hello, Milt.
Myself unmuted here.
Okay, yeah, so thanks everyone for coming back. So I do have some other poll questions. Like I mentioned before, we do need to do these poll questions so that we can have everyone that needs CEUs to qualify for it. So here is the first poll question. If you can just go ahead and quickly answer. Okay, yeah, thank you for that. So I can just quickly share the results here. And then we do have one other polling question here. Actually, looks like that's, oh yeah, here we go, this is it. Okay, here we go. So if you could just quickly answer this polling question, please. Okay, thank you. So we are going to move ahead. Our next set of speakers is going to be Randy Black and Milt Larson. Milt has served as a project manager and process treatment lead on numerous water quality evaluations, corrosion control, water distribution, and treatment projects. Milt has evaluated and designed treatment facilities for numerous groundwater contaminants, including PFAS, PCE, NDMA, DBCP, hydrogen sulfide, iron, manganese, arsenic, and ammonia. Milt is a member of PNWS Water Treatment Committee and AWWA's Inorganic Contaminants Research Committee, Corrosion Control Committee, and chairs AWWA Standards Committee on Scale and Corrosion Control Chemicals. He is a life member of AWWA and participated in the preparation of AWWA's Manual of Practice M64, Aeration and Gas Stripping, first edition, and M58, Internal Corrosion Control in Water Distribution Systems, fourth edition. And Randy here, let me get his. Randy has worked for Lakewood Water District for many years. He has also been very involved with AWWA, and it has served as the association director, board president, and has also been involved with basketball refereeing and has reffed basketball games for NCAA Division II games. So thank you to Milt and Randy, and go ahead and take it away.
All right. Well, good morning, everybody. As we usher in this new era of seminars and still helping people receive CEUs, this is a unique opportunity. And so I'm excited about the ability to be able to present this information. A little bit of background about our district here. We have over 60,000 retail customers and over 55,000 wholesale customers. We serve Fir Mutual Water Company, Summit Water and Supply, Rainier View, Spanaway, and town of Stillicum as well. We are solely a groundwater supplier. All of our sources are groundwater. We have 30 active wells, and the site that we're talking about this morning is our Ponders well site, which has H1 and H2 is the identification for the wells, and combined we do over 2,000 gallons a minute. Next slide. So this kind of gives you a little bit of an idea of the location of the site where we are talking about. If you've gone up and down the I-5 corridor, and before you either come to Gravy Lake Drive exit or go past the Gravy Lake Drive exit, on the southeast side of I-5, you'll notice previously some stack towers that were there. That is our Ponders well site. And so the site that we were contending with early on in the early 80s was the Plaza Cleaners. And we'll talk a little bit more about what happened there at the Plaza Cleaners. Next slide. So we early on in the early 80s detected PCE at the site, and so PCE was designed in the 70s as a solvent for dry cleaning process, and so the Plaza Cleaners was a commercial a laundromat and laundry service that served many of the businesses in Tacoma, Pierce County area. In the 80s, it was linked to the as a carcinogen and as a toxic pollutant. The maximum contaminant level, or MCL, was at 5 micrograms per liter. It is we found it obviously in the groundwater, and when it's in there, it's very dense and it's heavier than water. So kind of give you a little idea of what you're contending with. It can be removed through treatment and for drinking water use. Next slide. So our Ponders well site, as you can see here, there is the 2 white stack towers there, kind of in the center of the picture. Again, we have water rights for this site of about 2,800 gallons per minute, so we are not currently maximizing our water rights at that site. The annual production for this site is about 250 million gallons a year. But as I mentioned earlier, in 1980, 1981, after we were testing for some SOCs and VOCs, we discovered at that time having PCE at 18 micrograms per liter, and then we had TCE also as well at 10 micrograms per liter. And then we also had dichloroethylene that was detected. So what we decided to do was to do a 10-day pump test for both. And then we finally found that the PCE from 320 to 185 micrograms per liter. And then later we measured the TCE at 28 micrograms per liter. So this predates the VOC and MCL levels that we had at that time. So next slide. So at that time, given where we were and the detection levels that we had, we shut down that site immediately. There was a limit to the pressure in the area because of its location and to one of our tanks, our Nyanza tank. It also caused to have inadequate FAR flow in the area. We put in for and had an application for this to be declared a Superfund site, given the proximity of the dry cleaners and the process that they were using with the chemicals for laundry services. The EPA then agreed and it was accepted as a Superfund site, which we at that time the design was for air aeration and air stripping, and so that equipment was installed in 1984. The idea was at that time was that this site would only be used for about 3 years. And then back in 1985, a year later, they started to look at those sample results and said that we possibly would need to take up to 10 to 12 years for the site to help clean up the 2 chemicals that were there. However, in 2012, it was the 5th year of a five-year review by the Corps of Army Engineers and for EPA, and the level of detail that was resolved from those and seen from those reports was that now, given the nature of the chemical, that we were now looking to have to operate the air stripping towers for over 100 years. And this is obviously due to the soil configuration that exists in the Vashon Till, which is the shallow aquifer A that we're in here in Lakewood. Next slide. So we were, again, going back, this site was only supposed to be used for 10 to 12 years. In fact, the equipment was really looked to be only in there for a short period of time of life. But now fast forward 35 plus years, we have an aging site. And so what do? It was reaching its useful life. And we did have some maintenance. We did agree during that time period to take on the maintenance and operation with the site. And so we did have at one time there in early 2000, we did replace the packing within the stripping towers. We didn't have very good adequate seismic issues resolved at the design back when it was done in the 80s. We also had the pumps that were originally sized, the well pumps that we have. We have 2 submersible pumps there. They were designed to really pump into the system, and so they weren't really utilized, and we were burning a lot of energy because we had to pump through the stripping towers and then into a wet well from there, and then pick it up and then send it back into the system. There was also aging on the MC panels. There was the drives that were replaced also back in the early 2000s. We went to variable speed drives. So we did some maintenance on those, but again, we were dealing with a facility that was never meant to be in existence this long. And so there were some other things that made us nervous, which was the access to the clear wells you can see, which is in the middle picture here, was recessed to some degree. And so we were concerned of water quality issues around it as well. So we had to take some extra steps in making sure that we had chlorination happening. And you can see by the bottom picture there that you can see some of the delamination of the supports, and then obviously not the most sufficient way for earthquake protection on the stripping towers themselves. Next slide. So all of this being said, we ran into funding challenges, to say the least. Back in the late 90s, EPA turned the site over to the State Department of Health. They took over primacy of it, and the EPA did consider the replacement of the facility and maintenance. We did work cooperatively with them to see if they would continue to help with the state, but they declined to fund any of it. We did get an initial grant from the State Department of Health to look at the alternatives and to really evaluate the site. Does it make sense for us to continue to use the site? Would it be more reasonably attributed to possibly looking at moving the site and looking at another site? Those were another piece of the evaluation that we did at that time. And we also looked at just what the impact would be if we did run into a new site, and then what would the treatment level or what could be the issues that we run into as well. So at the end of the day, that study told us that we really had the best alternative to stay at the site, given that the water quantities and the flow of the aquifer. And so we now then had to work with the State Department of Health and Ecology to help with getting funding through the legislature, because again, this was really a EPA Superfund site, and then it was taken over by the state. And then the state said that, you know, we really had to work cooperatively with them to help get the funding to get the replacement. So we took on a ground roots program to educate local legislators and our representatives in the area here. And then we took it to educating the committees in the legislature, Budget and Finance Committee, the Budget and Finance Department, the Commerce Department. All those people had to be educated and understood as to why we were coming to the state for funding. So we were successful in 2016. We received a 1.5 million grant. It wasn't what we needed to really construct the whole site, but that's all we got that year from the legislature. And there was a proviso with that we had to spend the money within the 2 years of that budget in order to keep the money. So that meant that we had to do obviously the pre-design, which was obviously the first few steps, but we also had to pre-purchase the equipment because we did not have enough funds to fully develop and design the site and get the site out to bid. So that meant that we had to come back to the legislature in 2018 and again, beating on the doors, and you know, the old adage about the squeaky wheel gets the what. So we were able to get another 1.8 million from the legislature for the construction. But again, now we were already 2 years behind. And so the 1.8 did not get us through the total construction costs that we needed. But it was enough to get us going and started, and we had a very good relationship. We still have a very good relationship with the Department of Ecology, and they were very instrumental in telling us that they felt pretty confident that the funds could be available going forward. And that was the case, but the district was also prepared to pick up the difference in case it did not get fully funded. And so that's why we did go out for construction in 2018. And we were successful in 19 in receiving 2.2 million, which we knew was going to be in excess of what we needed, but we did have fully funded the construction costs. And so we're just about ready to close that out now. So this kind of gives you a little bit of an overview of the concentration levels that we were dealing with. And we do know that the aeration stripping is very successful. We have zero residual after treatment. And so this kind of gives you an overall about what we were looking at the time when we started in the 90s with the testing and what we were receiving through treatment and where we are today. So next slide. So again, the idea was too, when we looked at this, is that was there other forms of treatment that could be more effective than air stripping? And so we also wanted to have the potential to utilize all of our water rights because of our wholesale customers that we needed it for. And we have been successful over the years having no PCE or TCE in the water through the aeration treatment. So as I talked about earlier, I mentioned some of those different alternatives that we looked at, that we've got the state funding. And we also looked at different forms of treatment. Next slide. So these are a couple, these are all three of the pictures that we went and visited. We looked at some low profile forms of treatment, such as multi-stage bubbling aeration. We also looked at sleeve tray, shallow tray aeration, and a spray aeration. We also looked at granular activated carbon, and we also looked at membrane cell degassing as well as part of that, and then advanced oxidization as another form of ways of treating for PCE and TCE. Next slide. So we did, at the end of the day, after we had staff involved and we engaged with our consultants, Kenny and Jenks, ended up with going back to the air stripping. But we also decided this time to build the site knowing that we were dealing with at least 100 years of anticipated treatment, that we would go with something that would be there in the years ahead. And so we went with stainless steel stripping towers. We have they're 25 feet tall. There's two of those. We have them in 8-foot diameters. And we have two booster pumps now. We've gone to line shaft turbine pumps, and so those have been efficient. We updated and obviously enhanced our telemetry and system of controls, and made it conducive to the field operations that we have. The other thing that we did too is we did a prefabricated station to kind of help accelerate in the timing and delivery of everything and meeting our objectives, given that we had to spend money or we would lose it. And then we also added on-site hypochlorite generation equipment. And then we also added GAC vessels. So then we'll talk a little bit more about that. Next slide. So in amongst all that, what do you know? PFAS comes along. And how did that affect us? Well, as we all know, that the unregulated contaminating monitoring rule came in effect in 2013. And we didn't have any detections at the time. We were safe with that at the time. So we were testing at all of our different levels, our shallow, sea level, deep aquifers. And then Fort Lewis had a well that came up with 51 parts per trillion at one of its well. And as all of us know, that the lifetime health advisory level for PFOS and PFOA is at 70 parts per trillion. But later on, we did get results from McCord, and they certainly exceeded those at 3 of their wells. And they then moved on to shutting those down. And so we started to sample on a quarterly basis in 2016. Moving on to, this gives you an overview of the site and how we feel that our contamination is coming from JBLM. Next slide. This kind of shows the detection levels that we found with Ponder's well site. Our board decided to take a proactive approach, and we actually shut down the site back in 2019. and because of the levels we were seeing with the PFOS and PFOA. Next slide. So again, we decided to go with a GAC treatment facility for the site. Do you want to, Milt, talk about the different sites, the different types of treatment?
Sure.
Or, okay.
Okay, so as been discussed earlier today, there's 3 typical methods of treating for PFAS, being GAC, ion exchange, reverse osmosis, and there's always a potential blending. Wasn't really an option at this site, as also previously indicated. Reverse osmosis and nanofiltration is extremely expensive. And at the time we started working on this, I think there might only have been 1 ion exchange facility operating in the country. And I think it was operating in series with GAC. And we at that time, we were in the process of designing a GAC facility in Southern California. And looking at the options for disposal, basically with reverse osmosis, you got brine on your hand, as Pierre mentioned, that still has to be treated. Single pass ion exchange is basically incineration of GAC, either thermal reactivation or incineration. So just looking briefly at GAC and ion exchange, GAC has been proven effective over the years. It's widely used for PFAS removal, and it's particularly good for long chain PFAS, which is what our major concern was. As indicated, ion exchange has a smaller empty bed contact time, and potentially offers a longer life than GAC, and is particularly good with higher PFAS concentrations and short chain PFAS compounds. With GAC, you're looking at about a 10-minute empty bed contact. It's a little bit less effective with the short chain PFAS compounds. Total organic carbon can limit bed life, and you do need to backwash to remove the fines, because there's a fair amount of fines that show up, particularly when it's delivered. At the time, anion exchange was relatively new for PFAS with a very, very limited application. And other anions, as Kathy Swanson mentioned, can limit bed life. You do need a pre-filter in front of anion exchange, and the media itself is about 4 to 5 times more expensive than GAC. So, as Randy indicated, the Ponder site was shut down in the fall of 2018, and the decision was made to add GAC for PFAS treatment. The intent was to try to complete this design and construction in time for the peak season 2019. And that didn't give us any time for pilot testing, but we looked at some of the rapid small scale column tests that we previously completed for Eastern Municipal Water District, which had similar low levels of TOC. At Ponders, we're looking at about 0.2 milligrams per liter of TOC, and at Eastern, we had under a 0.5 milligram of TOC. And at that time, the Eastern well 59 PFAS and PFOA concentrations were a fair amount higher than what we had at Ponders. And so with the pilot testing that was conducted by our subconsultant at Eastern, we looked at both enhanced coconut shell and bituminous carbon. And we looked at 2 different models, constant diffusivity and proportional diffusivity. And these models are used to basically develop the media size used in the rapid small scale column test. And we were getting substantially longer bed life with bituminous compared to coconut shell. Roughly is about 4 times longer bed life. But both for the proportional diffusivity and the constant diffusivity. So what we ended up settling on was we put in 4 12-foot diameter, 40,000 pound GAC contactors with room set aside for 2 additional contactors for the time that the district goes ahead and puts in a 3rd well on that site. And in the background here on the right-hand side, we've got a backwash tank, 95,000 gallons used primarily for the initial backwash. They do have the capability of having a fluffing backwash if they do get a buildup of head loss over time. And basically, the carbon is installed in the vessels pneumatically, and they'll be similarly removed. And typically, the trailer shows up with 3 bays in there. One's typically empty and 2's full of carbon. So that, then they can. So when a change out, they basically empty out the vessel to the empty bay, and then they blow in the carbon from the full bay. In this case, since we got 40,000 pounds, it would take one trailer would fill a vessel. And this is what the site looks today with the 2 packed aeration units with the precast or prefabricated pump station and the GAC vessels and the backwash tank. There were a few issues related to the delivery of the GAC. The vendor didn't meet the delivery schedule, and then we also had a little bit of an issue where the GAC vendor was required to provide a template for the anchor bolts, and it turned out that the anchor bolt holes on the vessels didn't quite match up the legs, so we ended up having to scramble a bit to get them anchored down, and the also the pump station was a prefabricated, but being a prefabricated unit, it requires a certification from Labor and Industries, and Labor and Industries didn't quite meet our schedule as far as getting to the fabricator's shop, so it arrived on site late, and so we didn't quite meet the 2019 season, but it's been operating since January, and with non-detects, as Randy indicated, both on the PCE as well as on the PFAS compounds.
Hey, Milt, we're
Yes.
gonna need to wrap up here because we're running out of time.
Okay, I'm done.
Yeah, baby.
Okay, Jolene.
Okay, great. Yeah, thank you, Randy and Milt. Thank you for your presentation. We do need to move on, but if anybody does have questions for Randy or Milt, you can go ahead and type them into the Q&A box. We can respond to those, as the presentation goes on. So yes, please do go ahead and enter those in. So next, we're going to move on to our next speaker. So Beth Mendy is a water and wastewater engineer that has been with HDR for 5 years. Her experience includes surface water treatment plant process design and operations, laboratory analytics, water quality management, and regulatory compliance. So thank you, Beth, and you can take it away here.
Yeah, good morning, everyone. Thanks for taking the time to call in. Today, I'm going to be talking about a project that we are working on up in Edmonds, Washington, and it is designing a groundwater treatment facility with a residential appeal. So today I'll get into, we're currently in the design phase of the project, so I'll give everyone a little bit of project background. We'll talk about the treatment process selection. We'll get into site constraints and permitting requirements. We'll talk a little bit about the operation and maintenance of the site and the facility, and then jump to a quick summary. So a little bit of the project background. Olympic View Water and Sewer District, which is located in Edmonds, Washington, they currently receive water from the Deer Creek surface water source from their Deer Creek surface water treatment plant that treats 0.65 MGD. And then the other water that they receive is from Seattle Public Utilities. And so what they do is they use this Deer Creek water treatment plant to offset those SPU water costs. And so a couple of years ago, I guess it was probably back in 1992, Olympic View Water and Sewer District began looking at other sources that they could also use in addition to Deer Creek to offset those SPU water costs, especially in the summertime. And so as part of that development, the district actually purchased a residential property with a house on it to develop the well field and to construct a new groundwater treatment facility. So here's a little bit what the site looks like. It's just typical residential site with a 2-story single family resident house. And then as you can see on that same street is where the district's office is located. So just a couple blocks to the east. And then 2 of the district's reservoirs are also located on that street. So everything is pretty close. And then Deer Creek is probably about 2 to 3 miles from the district office. So jumping into a little bit about developing those groundwater sources and well sites, the district drilled the first well, which you can see labeled well 1. They drilled that well and tested, there's 2 aquifers, there's a confined aquifer and an unconfined aquifer. And so the first test that they completed was in the lower confined aquifer. And so that aquifer was found to have poorer water quality than the upper aquifer. And so there was ammonia and hydrogen sulfide, which really would affect the treatment process in terms of the chlorine demand and changes in chlorine demand. And so with that upper unconfined aquifer, it had much better water quality. However, there were high levels of iron and manganese in that aquifer. And so after the first well was drilled, then the second well was drilled a couple years later. And so overall the capacity that they could get out of those 2 wells from the upper aquifer was about 350 GPM. And so that's what they wanted to size this new groundwater treatment facility for. Jumping into a little more of the groundwater quality. So like I mentioned, there's high levels of iron and manganese, and so you can see those levels there. And so basically this water would be sent from the new facility to the 2 reservoirs that I pointed out earlier. And so that groundwater would then mix with SPU water. And so as you can see, the SPU results, there's very low levels of iron and manganese in that water. So jumping into the treatment process selection for iron and manganese, we looked at a couple of different options. So adding sequestrant was one of those options, which what sequestrant does is it disrupts the ability for iron and manganese to cause acidic issues in the distribution system. However, with the high levels that we had, sequestrant really probably wouldn't be very effective and could lead to black and red water issues with those compounds. And so typically that only lasts about 24 to 48 hours as a mask in the distribution system. And with those 2 reservoirs, water is likely to be, especially in the winter time, sitting in those reservoirs longer or around the 24 to 48 hour time period. So that option was taken off the table. The second option that we looked at was blending. So really just diluting the iron and manganese concentrations with SPU water. However, with the limited capacity that we have at the site of only 350 GPM, that really limited the amount of water that we could have been pumping to meet those secondary MCL levels. And so that option was also taken off the table. So the third option that we looked at was removing the iron and manganese with treatment. And so that was ultimately the selected option for the site. So we ran a couple pilot tests. And so as you can see here, here's the manganese removal results. And so the pilot testing was very successful. It showed that we could get those levels really far down from what they were below. So the Water Research Foundation goal is 0.015 milligrams per liter. And so we were able to get lower than that for the entire testing period. And then as far as iron removal also was very low and much lower than the goal that we were aiming for, 50% of the secondary MCL. So a summary of those pilot testing results: ran the pilot test for a single day, and over that day, the chlorine demand averaged about 0.6 milligrams per liter. And so that was the basis of the design for the new facility that we used. And as part of that, really paying attention to pH, there was a small pH drop, but nothing too major, went from 7.6 to 7.58 over the course of pilot testing. And so as shown in the graphs in the previous slides, the pilot testing really supported a reduction of iron and manganese concentrations. So jumping into a little bit about the filter design, the filters that were tested were pyrolusite filters, and the system to meet the 350 GPM capacity, there were 4 filter vessels on a skid. And so this is not a redundant system, as this source is really going to be used for offsetting SPU costs in the summer and then as an emergency source. And so if some of these vessels went down, the whole facility would just go down for that time period. The design flow rate, 350 GPM. Each of the vessels was 42 inches in diameter. The surface loading rate was 8.9 gallons per minute per foot squared, and that is during normal filtration operation. The empty bed contact time was about 1 minute during normal filtration, and then the backwash rate was 269 gallons per minute. And so a little overview jumping into more of the treatment processes. The main process is the pyrolusite filters, because that is removing the iron and manganese, which was the main water quality issue. We are also adding chlorine, sodium hypochlorite as a disinfectant. We're also adding orthophosphate for corrosion control, and that matches what the district currently feeds and uses at their Deer Creek facility. And then lastly, we are adding sodium fluoride, and that's also used at the Deer Creek facility and at SPU. So that's really just to blend and make sure that the water quality matches the existing sources that it's going to be blended with. And then lastly, we do have a backwash equalization tank. Since the site is so constrained, and we'll get kind of more into the site constraints later on in the presentation, but that backwash tank is really to hold the backwash from the filters and also from the blow-offs when the wells are started up. That way we don't, and they're going to eventually be fed to the sanitary sewer, but putting them in that backwash tank avoids overflowing that sanitary sewer. And so they'll be able to sit on site until they can be fed out to the sewer. So here's a couple quick model shots of the filters in the facility. So the 4 filter vessels and then the 2 wells come in combined and then feed through those vessels. Then they'll be fed with orthophosphate, chlorine ahead of the filters, and then sodium fluoride. And then here's a quick shot of the inside of the facility. So as you can see, the filters, the chemical feed systems, the electrical in the front of the facility. And this is viewing the facility from where you would access through the garage and access doors. So getting a little more into the backwash disposal, like I mentioned, the waste sources for this backwash tank are the backwash waste from the filters, which it's estimated that those filters need to be backwashed approximately every 24 hours of use. And so this facility really is estimated to run about 8 to 10 hours a day during the summer. And so really that could be 2 to 3 days before these filters have to be backwashed. And then also, as I mentioned, the well 1 and well 2 blow off water for when they haven't been started up in a while, just to feed those into the tank. And then slowly fed out into the sewer through an air gap. And so that tank that's going to be on site is 10,000 gallons. So quite a large tank, but that will provide at least 24 hours of storage if the filters need to be backwashed and the wells need to go through the blow off line all at once. So getting kind of into the bulk of the presentation, the site constraints and the permitting requirements for putting a facility in this residential area. So diving a little bit more into the project site, you can see here that the site is located on a cul-de-sac. The main access is through the arterial, so 228th Street Southwest. And so this site is owned by the district. They own the house, they maintain the property. Their water treatment operators can work on the landscaping and pretty much take care of everything there. You can see in the back of the property, there are some mature fruit trees. And so that is something that the district allows the residents to come on and pick the fruit and use the fruit as they would like. And so the district or the residents really have access to the full property to just go on whenever they feel like it. And the district currently has a covenant with those neighbors on that cul-de-sac. So there's 5 houses. And so as part of that covenant, there are certain requirements that the district can and cannot do to that site. And so that's really to fit into the aesthetics of the neighborhood. And so that was something that we really had to be aware of as we were going through this design. So when we first kicked off this project, we really needed to make sure, as part of building a treatment facility, basically on a site with a house, we really had to make sure that we were going to meet and address those neighbors and residents' concerns, or the project likely would not move forward. And so we kicked off a meeting with the residents and the members that are part of the covenant with the district at the district's office. And so we really talked about and dug into some of those concerns that they would have as we move forward. So some of those concerns were chemical storage and delivery. Is this, are there going to be large delivery trucks coming on site? Are these going to be hazardous chemicals? Those kind of questions. Also noise. The residents were there when the wells were being drilled, and they were concerned about what pumps, what kind of noise is this facility going to put out, and how's that going to affect them. Also access restrictions during construction. What kind of access restrictions are there going to be? Is this going to affect residents getting to and from their houses? Also just general neighborhood aesthetics of what is it going to look like when you tell people that there's a treatment facility located on this residential site. Also with frequency of maintenance vehicles, is the district vehicles going to be going to the site more frequently? Is that going to cause more traffic? Things like that. Also facility height and blockage. There's houses that are 2 stories, and so really if the facility got too high, that's really going to block their views, and that's not something that they're going to want to look at from their homes. And then also with lights and security, are they going to have lights that are blaring into their properties, or is this going to be something that is going to work for them too? And so those are kind of the things that we really talked with them about to see what they wanted out of that. So some of the facility features that we've included as part of the design to address those concerns of the neighbors were submersible pumps. And so we're going to be using submersible pumps for the well, so everything is below grade, and that's really going to help to limit the noise when this facility is operating. Facility vents for ventilation, those are all going to be facing the interior of the site to limit the noise from the facility. The garage and access door are going to be facing the main street so that all of the traffic is in and out from the existing driveway that you can see there in the photo. The facility and waste tank are governed by the neighboring homes, and so really this facility is being designed to look like a single car garage that is part of that property, and so that's based on a lot of the single car garages that do already exist in the neighborhood, and so that was how the exterior of the facility was designed. And I will show you a couple photos on the following slides. And then also really landscaping, like you saw, there's going to be a massive backwash tank, and really trying to blend that in with the neighborhood. We'll be adding some new trees and landscaping just to kind of keep people's eye away from that, so it doesn't look like there's a facility located on the site. And then also really being involved with the neighbors as we get to this final design stage of selecting the color of the facility, and little details like that that the neighbors may have opinions on, that it really doesn't matter what color the facility is. And so that's where we really want to involve them in that process. All of the lighting will be towards the front of the site. Chemical deliveries will be through the front of the site. And then there will be fencing to secure the site, and that fencing will blend in with some of the existing fencing that already exists in the neighborhood. So here's a quick shot of the facility exterior. You can see there's a garage door for trucks to get in and out, for equipment to get in and out, and then the access door. Then the lighting will all be in the front of the facility, and then on the side towards the home on the site. And then here's the other side of the facility with the backwash tank. There will be some new trees and landscaping put in behind that, just to have that blend in, so that the neighbor on the back side of the facility doesn't have to look over and see a large tank every time they look out their window. So as we got into more of the design of this project, some things came up in terms of site improvement requirements. And so as part of that, the permitting agency that we're working with came back with some additional requirements for frontage improvements. And so with those improvements, it was required that we were going to need to have sidewalks, planter, curb, and gutters on that cul-de-sac and on the main street. And so also as part of that, there was an access improvement requirement, and so which required more right-of-way from where the main street turns into the cul-de-sac. And so the additional requirement would be that access would actually need to be off of the non-arterial street, which is the cul-de-sac, which the access currently is from the main street. And that access point would need to be at least 50 feet away from the point of curve, basically the new right-of-way that we would be including in that curve in the street. And so here's a quick shot of what it would look like to add in the curb, gutter, planter, and sidewalk to that site. So as you can see, it really constrains the site even more from what it already is. And it also would require us to move a really nice set of mature hedges that kind of helps to hide the facility as it is now. So the current status of where we're at in design is we've submitted a couple deviation requests. And so those requests are to propose a lesser standard on that non-arterial cul-de-sac street. And so really instead of 7-foot sidewalks, a planter, curb, and gutter, we're trying to propose 5-foot sidewalks, which is what most of the cul-de-sacs in the area have, if they have sidewalks at all. And then we're also proposing to maintain the current access point on the site to what it is now, just because we don't want to have chemical delivery trucks driving down that cul-de-sac, and really to help meet the concerns of the neighbors. And so those are two things we're waiting for responses for. But we will be adding in a sidewalk, curb, and gutter on the main arterial street in the front of the site, because that whole street is going to be redone in the next couple of years. And additionally, as part of that, adding on the sidewalks, that's adding on a lot of impervious surface. And so that has triggered some additional stormwater requirements that we're going through and now looking at, which is going to require us to do some pilot infiltration tests and reviewing a couple more on-site stormwater management options. So jumping into a little bit of the operation and maintenance of the facility, but really I want to hit on the operation and maintenance of the site itself. So with the facility, we really want, like I said, it's only going to be used in the summertime. And so we really want it to be easy to start and shut down the facility. So that it's going to be sitting idle for a long time, and that it just makes it easy for the operators, since they will now have two different facilities, this one and the Deer Creek water treatment plant. And then as part of that, also managing chemical deliveries in this residential neighborhood, and really making sure that we can try to be efficient when those chemicals are delivered, the hours that they're delivered, so that they don't disrupt the residents in the neighborhood. And then really maintaining the landscaping. Like I said, the neighbors enjoy the fruit trees on the site and like to be able to go and pick the fruit. And so that's something that the district plans on maintaining, the flower beds, all of the landscaping on the site, mulching. And so those are all maintenance items that the district is going to have to keep up as part of also running and operating this facility. And then in addition to that, just maintaining a secure environment. This will be a facility, and just making sure that that is going to fit in with the neighborhood and not cause any safety concerns or draw any attention to that site in specific. So jumping into summary and conclusions, a couple tips of just things that we've learned throughout the process of this project. Really engage, I think the most important one is to engage the community and engage the community early. There are a lot of things from the concerns that we received from those residents that were very easy to address as part of our design. The fact that we knew those upfront and early, whether, as if we had pulled them in for 90% design, how would that have really changed our design and caused us to go back and do a lot of redesign if we hadn't done that upfront. And then really taking those concerns and discussing them and being able to apply them to the design features to mitigate the concerns of the surrounding residents. And then review impacts to surrounding areas and really be aware of the permitting requirements and start the permitting process early. So really working with the county to see what their concerns are and what they're going to require. So that way you're able to incorporate that as part of your design. So there's a lot of moving pieces and a lot of things to be aware of, but I think starting early, engaging the community are really, really the high priorities for designing projects in these residential areas, which is something that we don't normally do all the time. So with that, I will open it up for any questions that anyone might have.
Yeah, Beth, thank you. It looks like there is one question about what modeling program that you're using.
So that is just Revit, the modeling for the facility.
I'm not exactly sure. Let me, I'm going to go ahead and, oh yes.
Yep, so we're using Revit for that.
Okay, thank you. So any other questions that people have for Beth on her presentation? Well, thank you very much, Beth. And if you do have questions, you can continue to enter them into the question and answer box. If you have questions for Milt and Randy or any of our previous speakers, you can also enter the questions into there. If we don't get them answered live here, we'll try to follow up with some written answers. But so it looks like we are at our next break. So we will start back in about 10 minutes. If you could come back maybe a minute or two early before 11 o'clock, we'll have another poll for everybody to answer. And again, just one other reminder that to get CEUs, if you haven't already done so, go ahead and enter your name and certification or license number in the chat box. And that's what we're using to get you guys your CEUs. So we'll take a quick break and see you back here in about 10 minutes. Okay, so thank you for that. So next up, our next speaker is Brian Smith. Brian has been a staff engineer at Wilson Engineering since 2015, designing water and wastewater systems. Prior to that, he was a staff engineer at Tacoma Water in the Water Quality Department. Brian is a licensed professional engineer and has been involved in a number of AWWA committees through the Pacific Northwest section. So Brian, I will turn it over to you.
Thanks a lot, Julian. Well, thanks everyone for tuning in, and hopefully we got most people back here. Yeah, so let's see here. I think I can go ahead and share my screen. Pull my presentation here. Yeah, so my topic here, iron and manganese removal 101. Just thought it made sense to kind of get back to the basics a little bit. When I first got into looking at iron and manganese, I thought this would have been a helpful presentation, and so it's not necessarily the hottest topic, but it is relevant. You know, a lot of systems in our Pacific Northwest region have iron and manganese in their water, and so pretty relevant topic here. And as you saw in the previous presentation, Beth touched on a lot of good things there. But I'll kind of bring it back to the basics a little bit more. So to go a quick overview of the presentation that's coming at you, iron and manganese, we'll touch on some of the basics of it, the chemistry, potential
Brian,
health impacts.
Can I interrupt you for a second?
Yes, please.
We can't see your screen. If you can share your screen.
Oh,
Sorry.
let's see here. I thought I had that figured out. Let's see. Oh, it says host disabled participant screen sharing. Ah.
Sorry, I need to reset something, I guess.
Ah.
Let me do that. Sorry, guys. Well, Brian, if you want to keep going, I'll try to get this figured out here.
Okay. Yeah, my presentation didn't necessarily have a lot of exciting pictures or anything anyway, so maybe this isn't a bad thing. Although it does have some interesting stuff.
Okay, that should work now.
Okay, there we go. This looks promising. That. Let's see here. Does that look like it's working now?
Yep.
Okay, awesome. Okay, so overview of what this presentation will be about, and I'll try and keep this pretty quick and try and stick to our 11:30 end time here. But yeah, so some of the basics of the iron manganese, and then also touching on how do we remove it in our water sources, mechanisms, techniques for doing so, how do we operate those systems and maintain those systems, and talk about 2 quick case studies that are interesting, I think. So the basics, iron and manganese, 2 metals that are common in the Earth's crust. You see here elements 25 and 26. They often occur together, but not always. They're often in their dissolved state. They can also be in their particulate state. But yeah, we're often worried about it in the dissolved state. These are cations, positively charged ions. Listed some common redox states of them: manganese in the +2 or +4 oxidation states, iron in the +2 or +3. They can show up as without color in their more reduced states, and then once they become oxidized, this is often when we see the color, the typical brown, red, brown, black. I'd say they're common in groundwater, commonly occurring as in their dissolved form. They can also show up in surface waters, especially anaerobic zones of deep reservoirs where there's reducing conditions. It's a common state where you find manganese, especially. Let's see here. So to touch real quick on the health impacts, potential health impacts, the thing to remember, these are essential trace nutrients. So at low concentrations, they're a good thing. Everyone needs them. I think most of the needs are supplied by people's diets, but can get some from our water as well. Like is shown here, iron is needed at 10 to 15 milligrams per day, helps with oxygen transport in the blood. Manganese, again, low concentration that's needed for enzyme function and other things. High concentrations can have some risks, more so with manganese. There's some studies that it can impair brain function at really high concentrations. And there's also some studies about risks from breathing in aerosolized manganese, like in the shower. But usually the taste and the color are the driving factor. They're pretty, can be pretty egregious before they start to become health hazards. So yeah, so the most common reason they're addressed is because of their taste and odor. iron can have that typical rusty color, red, orange. It can have a metallic taste. And based on those things, EPA has set the secondary MCL at 0.3 milligrams per liter. Manganese, typically a brown or black coloration with that. Bitter metallic taste can come with it, and those things drive the secondary MCL of 0.05 milligrams per liter. I pulled out a blurb from the design manual, the DOH design manual, addressing how are these contaminants regulated. So there's different takes based on whether these are existing problems or new systems. And so existing, you can see here, existing systems that do not exceed the secondary MCL. If they bring on a new, say, source, a new well or something that does exceed the MCL, then they do need to provide treatment. The second bullet here is an existing system that already exceeds the secondary MCL doesn't necessarily have to treat if they bring a new source online. I found a little error in the wording, I think, in the design manual here, but basically they're looking for something saying that the customers are basically accepting of the current water quality problems, and then again also looking at the life cycle treatment cost information, but not so wouldn't necessarily have to if it's already an issue. And then the last bullet here, any new system does need to comply with the secondary MCL. Let's see here. So we'll kind of summarize 4 of the common removal techniques for iron manganese here. And as we'll talk about, I think one of these is probably the most common, but the other 3 are also relevant. So oxidation filtration is one way to get rid of iron manganese. Oxidize it and then filter it out. Related to that, but a little bit different in nuanced ways, is catalytic media filtration. And we'll talk about that a little bit more. Biological filtration can also be effective at iron manganese removal. And of course, reverse osmosis can remove iron manganese. As Beth mentioned in the previous presentation, sequestration is another technique to deal with iron manganese, but it doesn't remove the iron manganese. It keeps it in suspension and binds it up basically for temporarily, so it isn't reacting with other things. But I'm not going to touch on that in this presentation. So first removal technique, oxidation filtration. So this technique relies on oxidizing the iron manganese into a particulate form. That precipitation process does take some time. We'll keep that in mind. So there's a number of different oxidants that you could use to provide that oxidation. Aeration with oxygen, chlorine, either gaseous chlorine or sodium hypochlorite or other forms. Potassium permanganate is another common oxidant. And potentially could use ozone to oxidize your iron manganese as well. If you have really high source concentrations of iron manganese, you might need a sedimentation step. That's typically really high levels. We're talking up in the multiple milligrams per liter, 8 milligrams per liter. Then you might need a sedimentation step. And then you, of course, once you have these small particulate iron manganese, you got to filter it out. You can do that potentially with a dual media, a standard filter. More commonly, something like a green sand or a manganese dioxide, and could potentially use a membrane filtration, especially if you're a surface water source that could, remove your pathogens and your iron manganese. The next technique I'll touch on is is kind of categorized as catalytic media filtration, which is kind of the same idea as precipitation filtration, but the precipitation is catalyzed essentially by the media, so it doesn't require a big reaction chamber and long reaction times. Oh, I forgot to mention it, but to fully precipitate iron manganese can take quite a bit of reaction time. It can take up to about 20 minutes for iron, or even an hour for manganese for a full precipitation. But in this catalytic media filtration process, that time is greatly reduced, and actually the oxidation and precipitation can occur within the filter itself. So it doesn't require the reaction chamber and volume that would be otherwise required. It can also utilize some absorption within the media, so kind of multiple processes going on. So this is a really common technique, and we'll compare these techniques at the end, but this is what I've seen to be the most common way to remove iron manganese. So again, it relies on oxidants to both regenerate the media and oxidize the iron manganese. So common oxidants are usually chlorine, especially sodium hypochlorite, or potassium permanganate. And then it relies on the filter media, which is often some proprietary media, but usually some form of manganese dioxide, either ore or coated sand. And for each proprietary system, there's various loading rates, mechanics, backwashing requirements, removal efficiencies, but I think most of these are on the same order of magnitude, with some slight nuance differences in the manufacture of the system. The third removal technique to touch on is biological filtration. So this doesn't require an oxidant. It requires the microbes to have conditions such that that foster the bacteria to actually remove the iron manganese. So you can modify the conditions to foster those bacteria that will perform that function for you, using parameters like oxygen, pH, temperature, to optimize those conditions for the microbes. Yeah, so the bacteria oxidize the iron manganese, can form these dense precipitates that then get filtered out. One challenge with this is if you have both iron and manganese, the conditions that favor the removal of each of those are not necessarily the same. So if you have both, you might need a two-stage biological filtration to optimize conditions for iron removal and then optimize the conditions for manganese removal. So these can be a proprietary system, or you could purposely operate your conventional media filter in a biological method. Lots of literature on doing that. Won't dive too much into that. And then the fourth and last removal technique to discuss, reverse osmosis. So of course this can remove almost all of our suspended and dissolved components in our water. Downside to this technique is that it requires either remineralization of the water to make the water palatable and less corrosive, as well as or the other technique, instead of remineralizing, is to blend some portion of the flow around the RO unit. If you just got iron manganese and no other contaminants of concern, probably not going to be cost effective. But if you've got other contaminants of concern as well, that's when RO can be a more cost effective. If you've got hardness or chlorides or other things that RO is effective at removing, it might make sense. So just to recap on the treatment techniques here, we've got oxidation filtration, which can be effective, but to have a full precipitation can take a lot of time. So more commonly, the catalytic media filtration is used. It can efficiently remove iron manganese. It's cost effective, small footprint, no large reaction chamber that's needed, easily operated. Biological filtration is needed in that you don't need to add a chemical oxidant, but of course you're relying on microbes, which can be finicky and subject to process upsets if they don't have the right conditions. And reverse osmosis, it's effective, but it comes with high capital costs, high operational costs, the pumping costs to go with reverse osmosis. And you only produce on the order of 90% of the water that you originally pump, and you've got that concentrated brine on the 10% or so. So those are all downsides of the reverse osmosis. So as you can see, the catalytic media filtration, the pros and cons I list here really show that there's a lot of pros. It's pretty kind of the obvious winner here, and it's definitely the most common iron manganese removal system I've seen used. And so we'll just touch on the operation and maintenance of these kinds of systems, the catalytic media filtration systems, from here on for a little bit. So how are these systems operated? Fairly simple. You add the oxidant and it goes through the filter. When you're calculating your oxidant dose, you need to account for, of course, your raw water has some oxidant demand that will take up the oxidant right away. You also need certain residual, certain chlorine or permanganate residual within the media in order to do that continual regeneration of that media to keep it catalyzing that reaction. I think often that's on the order of 0.5 milligram per liter of chlorine in order to keep that regeneration going. And then of course if you're also using your chlorine, typically chlorine for your distribution system residual, then you need enough at the end of your filter to provide that. And then within the filters themselves, just listed some common loading rates. 5 GPM per square foot is pretty common, can be effective, still up at 10 to 15 GPM per square foot. Let's see here. Another slide here on operation. The other big operating parameter is the backwash. So the backwash flow rate depends on what kind of media you've got there. Manganese dioxide is a more dense material, and so you need a higher velocity through your backwash, through your filter backwash than say a green sand that's a less dense material. There's a number of different methods of backwashing, which I think are kind of neat. This one here is showing that if you've got multiple vessels, you can actually use your source water. You don't need a dedicated backwash supply or to pull from your distribution. You could use your source water to come through, feed through all of your filters except for one, and then that source can provide your backwash flow. Let's see here, but that's going to shift the pressure, and so where your operating point is, so you need to account for that. That worked well with constant flow rate sources. It's a little more challenging if you've got changing flow rate in your source or multiple sources because you really need to maintain a set velocity through that filter, set flow rate through that backwash to make it effective at backwashing off the particulate iron manganese. Of course, you can backwash instead of from your source, you could backwash from a dedicated backwash finished water tank or from your distribution system back through your backwash. Often these systems require each filter about 5 minutes of backwash for every roughly 24, 48, sometimes more hours of operation if it's a pretty clean water supply. That can be triggered by differential pressure across the filter or total flow if you know how your system operates pretty well. And then of course you got to dispose of that backwash. Often if you've got a sewer available, that's a good method to dispose of your backwash. There are some systems that use drying beds or other things like that, and then landfilling of those solids eventually after they accumulate for a while. And to touch on the maintenance aspect of these systems, you got to maintain the equipment, of course. Equipment consists of automated backwash valves in order to provide that backwash, and those can be either actuated either pneumatically, hydraulically, or electronically. And then the systems that go with that. So, you know, for a pneumatic actuated system, you've got your air compressor and things like that. Of course, you've got to maintain your piping and your vessels, especially coatings. Got to maintain your oxygen dosing system. And one consideration that's a nice one to keep in mind when setting up these systems is if you can keep your oxidant, your sodium hypochlorite or other oxidant, separate from the rest of your equipment, it'll increase the longevity of your equipment. So it's not such a corrosive environment for that equipment. And then of course your media, you need to maintain backwashing. You know, you shouldn't be getting a lot of media loss during your backwash, but it will slowly over time deplete your media a bit. So you can keep an eye on that, and maybe every 5 years or on something on that order of magnitude, do a little bit of media replenishment. So I had this section for questions. I don't know if I'm not seeing any questions at the moment, so I'll just jump into these. I got a slide here on a number of common manufacturers of the catalytic media filtration systems. ATEC is a common one. They're based in the Northwest here. There's a lot of their installations in the Northwest. Some other manufacturers also make these systems: Water Surplus, Filtronics, AWWA, and Tonka. And then real quick here, got 3 minutes, looks like. I'll touch on these 2 example projects. Here's a picture of the existing system. This is an existing system installed almost 20 years ago. The treatment equipment, and especially electronics that go with it, are kind of nearing the end of their life, and so we're looking at replacing that. Currently it's a 30 GPM system. We're looking at upsizing it to a 60 GPM system. Their source water doesn't have any iron, does have manganese at more than 2 times the secondary MCL. And so for this system, this existing system is one of the original Filtronics systems. It's kind of an interesting system. It seems like kind of a hybrid between the oxidation filtration method that I talked about and the catalytic media filtration, in that it does have these 2 reaction chambers. So there is some contact time where that precipitation is encouraged of the manganese, but it's not, you know, enough time. It's not an hour, like I said, for a full precipitation. And so it does have this this media that I think is catalyzing the reaction as well. But it's a little bit of a hybrid system. A lot of the systems these days don't have these reaction vessels. There's not much contact time before it hits the filters. Anyway, so but this project is kind of a fun one. We're kind of phasing the improvements. So we're replacing the treatment equipment now. The pumping equipment is still in reasonable shape, so we're upsizing this. We're getting a little bit more flow out of the existing pumps, but we won't get the full capacity of the treatment system until the new pump, the next phase of the project replaces those pumps. So that's kind of a fun one. Another quick example. This was on an existing water system that had some iron and manganese. The iron was below the MCL. The manganese is just a hair above the secondary MCL. They decided they wanted to do iron manganese removal. This is a 160 GPM system. They had 3 well sources, which kind of makes the backwashing system a little bit more nuanced, a little complicated, but it works. We also had this air stripping system for corrosion control just downstream of the iron manganese removal, and so that made the backwashing a little bit interesting because it discharged into this low head tank, and so in order to facilitate the backwash, we had to add a pressure sustaining valve to add back pressure in order to direct the water into the backwash filter instead of going to the production. And then of course we had to make sure that the flow rate during a backwash was sufficient, especially with those multiple sources. And so we actually had the distribution system supplemented the supply flow during a backwash. So it's kind of a fun one. Looks like I'm about out of time here. See if there's any questions. I'm not seeing any here. Well, thanks for listening along, everyone. Hope that was
Thank you, Brian. I also don't see any questions here, but if you guys do have any questions, you can go ahead and put them in the question and answer box. That was a very interesting presentation, Brian. Thanks for going through that for us. So we're going to move on to our next presentation. I did notice that there was a different poll that we had wanted to run through previously. But so I will introduce our next speaker. Our next speaker is Lee Odell. Lee is the president of Odell Engineering. He has 30 years of experience as a consulting engineer specializing in water treatment and 4 years experience as a water treatment plant operator. He has developed and teaches 5 courses on water treatment for the American Society of Civil Engineers, and he is also the author of the AWWA book, Treatment Technology for Groundwater. So I'll just quickly share the results on the poll here, and then I will turn it over to Lee.
Great. Tell me if you can see my screen.
Yep, we can see that.
Okay, great. So I'm going to talk about optimizing manganese removal. So great lead in by Brian. And we're going to talk a little bit about manganese because it's very common. About 1/3 of water utilities in the US are above the secondary MCL of 0.05. And it's commonly found in a reduced form in groundwater and can be oxidized by exposure to a number of different oxidants. So the reduced form is manganese or Mn+2. The oxidized forms are Mn+3 or +4, and even higher oxidation states for permanganate. But normally CO2 works to dissolve manganese in minerals and forms manganese bicarbonate compounds, but sulfate reducing bacteria can also be present. So you might have manganese sulfide compounds, or you can also have organic complexes with the water. So why do we want to remove it? Brian gave a great example. You see discolored water all over the places. There's also a lot of concern about buildup of manganese scale in distribution pipe, and that scale will periodically release large volumes of material and cause discoloration events, and a number of different things can trigger that. There's also a lot of new health information that shows it may have a neurological effect in children. So just last year, Canada updated their maximum allowable concentration, and they established both a primary health level, they call it a MAC of 0.1 milligrams per liter, as well as a lower aesthetic objective of 0.02. And that 0.02 level is really there to prevent scale buildup in the distribution system. So I'm going to cover just the different removal mechanisms to get manganese out of water. and then talk about each one, maybe what the key design criteria are, things to think about to optimize removal, and some concerns or potential pitfalls with each one of those. So first, removal mechanisms. There's a lot of different ways to get rid of iron and manganese removal. If you do any research, you'll see all kinds of different ways. Some of them they say are proprietary and don't want to tell you how they work, but there's really only 4 ways to get rid of manganese from water. You can exchange it in a cation exchange process. You can uptake it with a biological process. You can precipitate it and remove the precipitate, or you can adsorb it onto oxides in media. So let's talk about each one of those. Ion exchange first. The removal process for manganese is the same thing that you use for water softening. It's a cation exchange process. Calcium and magnesium are present in water as divalent cations, and that's the same form that manganese in its reduced form is present, as well as iron in its reduced form. So the same process that you use for calcium and magnesium removal in cation exchange is also potentially available for manganese removal. For ion exchange design criteria, it's really dominated when you size the vessels by the calcium and magnesium removal. So they supply that when you talk to ion exchange suppliers about softening, they all want to know how many grains of hardness you have. So grain of hardness is 17.1 milligrams per liter as calcium carbonate. You can convert your hardness in the water to grains, and they'll tell you what size of a softening system you need for that. Loading rates typically can be 8 to 12 gallons a minute per square foot. 10's very common for ion exchange softening. The size and number of vessels are really based on the total resin volume and how frequently that you might want to regenerate the system. So just for example, 500 gallon a minute well with 150 milligrams per liter of total hardness is 8 grains per gallon. Typical resin capacity is 30,000 grains per cubic foot. So you can do some quick math. I showed my work over here in the table, and with a vessel size of 6 foot diameter, you would need 2 of them in order to have a total resin capacity of about 8.5 million grains. And that would give you a regeneration frequency of 32 hours. You typically regenerate them with salt and an application rate of 10 to maybe as high as 18 pounds per cubic foot, depending on how much organic carbon's in the water. The brine strength is usually around 10%, so that's diluted from a pure saturated brine concentration. And then the backwash rate is part of the regeneration, part of the waste. So that's based on the density of and size of the resin that you use. Really, if you're trying to optimize ion exchange for manganese removal, there's a few things to keep in mind. One, you don't want any oxidants ahead of the ion exchange system. So you don't want to have any oxygen exposure. You don't want to have like you're pumping to a tank. You don't want to pre-chlorinate. I've seen both of those occur. A lot of these softening systems are put in homes, and they're already exposed to oxygen and chlorinated, and they do a terrible job of iron and manganese removal at that point. The iron is typically already oxidized, and the manganese is maybe partway oxidized out in the system. So they really need to be right at at the wellhead and before anything else happens to get good iron and manganese removal. Also, it's hard to remove iron and manganese in ion exchange. There's a lot of folks that recommend different levels. About 0.5 milligram per liter of total iron and manganese is one recommendation that I like. I've seen people say you could remove as high as 10 milligrams per liter of iron and manganese if you have really hard water, but I've in ion exchange systems that have iron and manganese, I see fouling of the resin a lot. So you should be prepared to clean it, acid rinse it, replace it periodically. There are also taste and odor issues that occur with ion exchange. You're replacing all that calcium and magnesium with sodium from the salt. So it's gonna probably taste funny to you. And in water softening, it's very common to bypass some of the water around the softener to make it taste better. But if you have iron and manganese in that process, you probably have to treat all of it to get down to the level that you want. So it's not very commonly used in municipal systems, and taste and odor issues and fouling are very common with it. There are some other things that you can use to regenerate with: potassium chloride, and even some sodium bicarbonate can be used. So there are other things as well that maybe don't have as big a taste. Chemical storage sizing are important. Brine depends on the size of the system. You want to look at your max flow and your average flow, and how much brine you're going to use and how frequently you're going to regenerate it. The saturated brine concentration is typically about 26%. You use about 10% for regeneration, so you need a method to dilute it. And typical application rates are 10 to 18 pounds per cubic foot every time you regenerate. So you can use a lot of salt. Brine disposal is getting more difficult to permit. Even through sanitary sewers, a lot of places have discharge requirements that have EDS or chloride limits. Biological manganese is another way to remove it. It's not always easy. The largest plant I've been to is Lake Havasu water treatment plant. That's a 25 MGD design capacity. It doesn't operate at 25 MGD. It operates at about 10 MGD with a filter loading rate of about 1.3 gallons a minute per square foot. And the water goes through this cascade aerator. It's picked up in a Rani collector. It has a fair amount of manganese, about 2.5 milligrams per liter. Goes through this cascade aerator and then into these large gravity filters that are just sand filters that manganese has built up on the coating on the outside of them over time. And it works very well. It works great because it's got a low filter loading rate, and it's been operating for a long time. The water quality is very steady. The sort of key to manganese removal are, one, having a long contact time. This is just a paper that was done on 10 groundwater treatment plants that remove manganese and showed just first order removal rates versus empty bed contact time. So, so the takeaway is having 10 or more minutes of contact time in a bed is probably a good practice for manganese removal. The other thing to keep in mind is there are specific oxidation states that the manganese bacteria like. So depending on the pH, 8 to 9, a positive oxidation of 300 to 500 millivolts or 200 to 300 millivolts. And just to give you an example, saturated with oxygen water is kind of in that range. So this is 300 to 400 millivolts. So highly oxidized water, pH is up to 8 to 9 for manganese removal, biologically is important. With manganese is way harder to remove biologically than iron is. And this is a test I did on some equipment for EPA, 6-month test, and the manganese would slough off all the time. So a change in flow, just, you know, hard to figure out what the reason was. But one day we'd come in and everything would be looking great, come back another day and the water would just be coffee. So I think unless you have very steady water quality and just really conservative filter design, like Lake Havasu, then you have potential upsets with that. So precipitation, Brian talked a little bit about precipitation for iron and manganese is a little bit slower than iron. Typically, we're taking this Mn+2 that's in the reduced state, and we're trying to oxidize it with the various oxidants, or we can raise the pH. And you can see all these little S's around the chart here. Those are all solids. So if you can change it from +2 by either raising the pH or increasing the oxidation state, you can form MnO2 precipitate or various other compounds that you can precipitate out of water. And manganese oxidant is pretty, you know, straightforward. There are lots of ways to oxidize manganese. Everything from oxygen to chlorine to oxide work. And oxygen is very efficient. It takes very little oxygen to oxidize manganese. However, it takes forever to make it go. So the other part of it is the kinetics. And oxygen really is too slow to oxidize manganese in any kind of a water treatment plant setting. Even chlorine can be a challenge. So this is an oxidation study that Bill Nockey did way back in 1990, and for various pH ranges, if you have a pH of 9, chlorine can oxidize manganese in 30 to 60 minutes, about 60 minutes for complete oxidation. But if you lower the pH to 8 or 7.5, that oxidation rate just slows way down. So that's a key thing with trying to precipitate manganese, is getting it to actually oxidize and precipitate. Even with potassium permanganate, pH plays a big role in how quickly that occurs, as well as things like dissolved organic carbon. The more DOC you have in the water, the slower the reaction time a bit. But potassium permanganate can react a whole lot quicker than chlorine does. So typically, if you're trying to precipitate manganese, some stronger oxidant than chlorine is very often used. One of the concerns about precipitating iron and manganese is that the particles that you form are very small. So they're on the order of 1 to 2 to 3 microns in size in general. And that means you have to generally have a pretty conservative filter loading rate. A loading rate of 3 to 5 gallons a minute per square foot is typically used. And then a typical schematic might be chlorine plus permanganate. Maybe you adjust pH a little bit. Sometimes a contact tank is needed to get that oxidation to occur, and then onto your filter. The design criteria for that: chlorine, you can figure out from pilot or bench testing, but really understanding the dose that it takes to oxidize it is very important. And then you can size the rest of the equipment from that. The permanganate, you can also do pilot or bench testing to look at how much of that it needs to oxidize manganese. If you're going to adjust pH, you can do that bench testing, titrations, or use a water quality model like WaterPro to figure that out. And then if you need a reactor vessel, that is something that you can pilot test it, but a lot of times people will just calculate how much time they want, put a baffling factor in, and size it that way. Filters generally used for filter surface loading rate. It's kind of the key thing. So 3 to 5 gallons a minute per square foot. You can size horizontal or vertical filter vessels based on that. And then backwashing. Oh, what happened? What was that? Let me see if I can reshare. Did somebody else share their screen?
No, it looks like it's your screen.
All right. Well, so backwashing is just gallons per minute per square foot times the square foot of the filter vessel, gives you a backwash rate. The frequency of backwashing you really need to do by pilot testing, and the duration could be 10 minutes or reduced if you have some air scouring associated with it. Some of the pitfalls with precipitation are really getting the oxidation rates right. I see, you know, this is kind of a conservative design for iron and manganese. So you see some places where they just kind of follow the Penn State standards or state protocol for designing these things, and they move ahead with it. But I've seen some, you know, multi-million-dollar treatment plants that don't work because they didn't have the right oxidation or contact time ahead of the filter. So it's really important to at least do some bench testing if you're going to precipitate iron and manganese to make sure you have the right dose and the right contact time and pH adjustment if you need it. Organic complexing can form little colloidal manganese particles that are really hard to remove or precipitate, have very slow reaction times. Ammonia can have a tremendous effect on chlorine dose. Organic nitrogen can be an interference that causes not just chlorine demand. If you do DPD test, it may show up as a actual chlorine residual, but it doesn't have any oxidation potential, and it also can have some taste and odor issues. So that's something to look for. Pore mixing can be a problem, and then just other taste and odors from organics or hydrogen sulfide that causes a metallic smell. So pilot testing is great. Those are a good way to identify all those ahead of time, but not always done. So lastly is adsorptive removal, and Brian also talked a little bit about that. There are a lot of plants in the Northwest that use adsorptive processes for manganese removal, and it's probably the dominant way to remove iron and manganese in modern plants anyway. Some of the things that you are looking for ahead of time before you design the plant are, again, you want to get your chemical feed doses right. You want to look for removal effectiveness with pilot test, identify a filter run length before you have to backwash it. But with adsorptive removal, you can oftentimes really maximize the surface loading rate on the filters. So it's not uncommon to have 8 to 10 gallons a minute per square foot. There's a few plants that are operating at even higher loading rates, up to 16 gallons a minute per square foot. And the thing about adsorptive removal is the flow process is very simple. This is from a pilot test that I did in December, but it's just chlorine injection and then right through the filter. And you can hear, in this case, we were testing multiple different medias, but it's very simple. It works at low pH. You're not trying to precipitate the manganese. You just want the chlorine to oxidize the media, and then that oxidized media will pull the manganese out of solution as it has that surface reaction with the manganese dioxide on the media. So this is from that same pilot test. Keep a chlorine residual of about 0.5 milligram per liter. And the manganese removal is pretty steady. In this case, we're getting about a 24-hour run. You can see the manganese start to break through and spike up before backwashing. If you don't keep the media oxidized with adsorptive media, whether it's green sand or pyrolusite, or just you're making your own oxidized coated media, it will lose adsorption capacity. This is from a test that we did over in Vancouver at a fish hatchery, and started the media soaked in permanganate, but then we couldn't have any chemicals while we were running it. You can see just over several weeks, it kept losing adsorptive capacity, and the finished water manganese kept creeping up and up. So periodically, if you could regenerate it periodically by soaking it in permanganate, and some places do that, but you have to keep the media oxidized for it to maintain an effective removal capacity. And the nice thing about these adsorptive media is you can get some really cost-effective systems. So this is a plant back in the Midwest. It's several years old at this point, but it's 4,000 gallon a minute plant that had a construction cost of $3 million. So they make pretty effective ways to remove iron and manganese, even with some larger plants. A couple other pitfalls to watch out for are, it's really infrequently, but sometimes the media will grow to a pretty large degree. And once the media starts to grow, you may not have enough backwash flow to effectively clean the filter. And that can be a problem from a performance perspective, but it could also have some biological activity in this media coating and can lose adsorptive capacity. So that's something to keep an eye on, and just monitor your media periodically. I'd say of a couple hundred of these plants that I've been involved with over the last 20 years, I've seen it maybe 4 or 5 times that's occurred. So it's pretty infrequent. The other thing that can occur is silica can adsorb onto the coating of the media. So manganese dioxide can react with silica. It tends to be an issue if the pH is up above 7.5 to maybe 8, 8.5. And that's something that you can test during pilot testing to see if the silica is adsorbing on the media. And if it is, there's ways to mitigate it, typically with a little bit of permanganate addition. But that's an issue that's kind of different for adsorption than it is for precipitation. All right, wow, 1 minute to spare, perfect. Thank you everybody for listening, and if there are any questions, I'll try to answer.
Yeah, thank you, Lee. So I don't see any questions in the chat box. If anybody does have questions, go ahead and enter them in. And it does look like that since we had to restart the Zoom meeting, everyone who, if you need CEUs, we need to get those entered into the chat box so that we can be sure to give you guys credit for this. So I do have one last poll question here. And we are going to be having 2 more sessions, probably in July and August. And so we'd like to know your interest in how likely you are to attend these next 2 sessions. We are also looking for your feedback because this is kind of the first time that we have done this. You know, we are looking to get your feedback on whether or not you thought this was useful, what improvements we can make. Definitely we'll try to not have somebody else cut our meeting off in the middle of it. And I just want to say thank you to all of the presenters that presented today. And again, if you have questions, please let us know. So I will just go ahead and share the results here, and please do keep a lookout on your email for the announcements for the next 2 sessions here. And with that, let me just, I was just going to share one last thing here. So thank you very much again. And let me, there we go. Oh, share my screen. Yeah, but thank you, and everyone stay safe, stay healthy, and we'll see you all again soon, and I hope that you have a good week.